So far we have dealt with thermodynamics, but thermodynamics is one aspect of conducting chemical reactions. Whether a reaction is spontaneous or not is told to us by thermodynamics. But even if a reaction is spontaneous, the speed at which reaction happens is important as well. Let me give you an example. If you want to turn a paper into an ash, you have two options. You can turn a paper into an ash by setting it on fire, and in a few seconds it will turn into paper ash. Or you don't do anything to it and come back 50 years later and it will crumble and it would have turned into ash. So those are your two options. What's the difference between those two options? The difference is basically time. One is happening quicker than the other. Making it react with oxygen by setting it on fire is a much faster reaction than not doing so and allowing it to slowly degrade and turn into ash. And in chemistry, the study of the speed of reactions is called kinetics. How fast a chemical reaction happens is important because we will not be carrying out reactions to produce the products we want if the reaction is very slow. Instead, we would look for alternative ways of carrying out chemical reactions where we can speed up the reaction. And there are certain ways by which we can speed up the reaction, which we will discuss towards the end of this topic. And so thermodynamics, apart from thermodynamics, the topic of kinetics is also very highly relevant. Let's look at some ways by which we show the kinetic information in a chemical reaction. Here, for example, you have molecules of A turning into molecules of B over time. A very simple reaction, one reactant A turning into B. So what happens over time? A gets converted into B. The product starts to appear while the reactant starts to disappear. And over time, if we were somehow to monitor the concentration of the reactants and the products, or how many molecules of A we have and molecules of B, we would notice something like this, where the concentration or the number of molecules of A is going down over time. At the same time, the amount of B is increasing. While this is a graphical format, here is another way of showing the same data, where we have originally 40 red and 0 white. If this was some kind of a reactant, over time, after some time, we get more, we get some product, 10 white and 30 red. Now we lost 10 red, turned into white. And after some more time, we have more white, less red, and eventually we are in a situation where we have mostly white and little bit red. If we give it enough time, it might turn into all white and no red. So those are just graphical ways of representing the data, graphical and pictographical. But here is an actual way that you can monitor a reaction, whether it's progressing towards forming the product or not. If we have some kind of a dye which can change color as the reaction progresses, or maybe the reactants itself changing color as the reaction progresses, then just monitoring the change in the color tells us that we are moving towards the end of the reaction, towards the formation of the product. There are more complex way to actually measure the concentrations of the reactant and the product by noticing the intensity of the colors, but we will not be looking into that. And here is a chemical reaction, methane reacting with oxygen gas, an exothermic reaction producing carbon dioxide and water. In this reaction, we are breaking CH bonds in methane and OO bond in oxygen gas and producing carbon-oxygen double bond here, 2 of them, and oxygen-hydrogen bonds, altogether 4 of them here. So we know from thermodynamics that bond breaking requires energy and bond making releases energy. Ultimately, this is an exothermic reaction, meaning that the amount of energy released by making the bonds is greater than the amount of energy required in making the bonds. And we also know from thermodynamics how reactions happen. Basically, the molecules collide into each other randomly, and sometimes they have just the high energy high amount of energy required to cause the bonds to break when they collide into each other and the new bonds to be made. So that's how a chemical reaction takes place. But as we try to investigate kinetics, we are going to go back to that energy diagram we saw previously, where we had placed the exothermic reactions where the products were lower than the reactants. Well, we will use the same diagram but with more detail now, and let's actually look at that diagram and then we'll come back to that slide. Here are our reactants and here are our products. This is clearly an exothermic reaction because the reactants are higher than the products. Okay, think of this as being methane and oxygen reacting to produce the products which we had here, carbon dioxide and water, C and D. But there is more detail here. We are going through this curve, this steep hill, and the height of this hill is equal to a certain amount of energy, and that energy is known as activation energy. You see, just because a reaction could be spontaneous doesn't mean it just happens. You may have to supply certain initial supply of energy. For example, gasoline, if it's ignited, it will spontaneously burst into flame, and if you have a large amount of gasoline, it will explode. Accidents like that have happened at gas stations in the past. But there is this initial supply of energy required, right? Whether somebody throws a lit cigarette there or a lit match there, or if you are driving a car, you need to boost your car engine by first supplying it with energy from your car's battery. So that's the initial supply of energy, and that is, in the context of chemical reaction, is called the activation energy. Activation energy, once it's supplied, then the reaction is an exothermic reaction leading into the products. And at the top of the activation energy, here at the top of this curve, you have something known as the activated complex, which is not an actual product, but just as the reactants are turning into products, it goes through that transition state there. So we have the activation energy, which is the minimum amount of energy required to initiate a chemical reaction. And at the top of the activation energy graph, you have an extremely unstable, short-lived complex there. On the other hand, if you have an endothermic reaction where the enthalpy of the products is greater than the enthalpy of the reactants, as we see here, where the products are placed higher than the reactants, here is the activation energy as well. So basically all chemical reactions require activation energy. Now ultimately, the speed with which a reaction happens depends on the amount of activation energy. If you have a reaction that requires a lot of activation energy, where this up climbing hill is very high, then the speed in which the reaction will happen will slow down. On the other hand, if the activation energy is very small, the hill is very low, then the speed with which the reaction happens is going to be very quick. There are other factors that also affect the rate or the speed of the reaction, and we will look at each of them in the next video.